topic today is graphing polar equations. So how do we get these polar graphs? We've already seen a little bit of this, at least the general idea of it. In our last one, we were talked about just polar coordinates in general. But today we're getting into more of how do we graph these, what's the process, and what do all these graphs look like, and what are the different common shapes that we can make from this. So let's get a whiteboard open. So the first thing, let's have an example of r equals sine of theta. All right, so if we don't know what a graph looks like, we pick typically x's, we find our y's, we plot the points. So for this, we're going to do the exact same thing, except we're going to pick thetas and we're going to find r's. So 0, pi over 6, and actually let me get rid of it this way, and I got a lot of numbers, so I'm going to make it a horizontal chart. And make that 3 look a little bit better. We do pi over 2. Now, we don't need to list everything for this next one. We can, since we know about our symmetry of our sine graphs and with the unit circle and how those are related, let's jump straight to pi. Then we'll do a 3 pi over 2, and then 2 pi. Although actually, we don't even need to get out that far. All right, so sine of 0 is 0. Sine of pi over 6 is 1/2 of pi over 4 is square root of 2 over 2, which is roughly about 0.71 or 707. Then sine of pi over 3 is square root of 3 over 2, which is about 0.86. Then 1, we're back to 0, -1, and 0. All right, so let's get these numbers and let's start drawing. So what I'm going to do is make some polar graph paper. So we're going to go 1 unit in each direction. There's 1. There's 2. Actually, we don't even need to go any further than that, but let's make each of those a half. So that should be good. And then we're going to put in a 45-degree angle and another reference angle 45 just to help us draw a little bit better. All right, so let's make this even bigger. All right, so starting off, when our theta was 0, r is 0. So we're right there. When we look at, let's put references on here. When we look at the direction of 30 degrees, we're going out 1/2. On 45, we're about 0.707. And at 60, we're at like 0.86. Then we're up at 1 whenever we're looking at 90 degrees. So keeping in mind how this all works, we're going to spiral out from here to that. And now, once we get to 90 degrees, we start working our way back down to 0. So we get something like that. And actually, that was kind of bad. Let me redraw that a little better. And we get a circle. Now, if we look down at our direction of 3 pi over 2, our value is -1. So we're looking down here, but we go 1 in the opposite direction, which gives us a point up here. So it overlaps. So from 0 to pi, we do this, and then pi to 2 pi, it goes around a second time. So our graph of r equals sine theta is a circle. goes through the origin or the pole, and it is going up and down. But that's going to be our process for drawing these. You pick your thetas, then you are going to plug them into your equation, and then you're going to graph them. So, but before we get into any more of this, let's talk about symmetry. Now, with our graphs in rectangular coordinates, we have three different ways to do symmetry. We can have x-axis, y-axis, or origin. Let's go ahead and see what happens with our polar stuff. So, with x-axis symmetry, we had a point up there and a point down there. Now in polar, we can do this as well. Our r's will be the same, but one has a positive theta and one has a negative theta. So if we're going to check what we call polar axis symmetry, what we would need, and this is going to be similar to x-axis symmetry, because it's a polar axis is the x-axis, the positive x-axis at least. We're going to have an r theta, and we're also going to have an r negative theta point always. So anytime we have r theta, you're guaranteed r negative theta. Next, we have y-axis symmetry. So a point here is the same as a point there. So in polar, it would look like this to get to them. And we're not going to base things off of our polar axis anymore, but if we do it off of the line y equals pi over 2. So this is symmetry about the line theta equals pi over 2, which is going to be the same as y axis symmetry. In this case, we're going to have an r theta point, but then we're also going to have an r pi minus theta point, because the angle we went through here is also going to be the angle we go through there. So we're using our idea of supplementary angles and how they're related with sine. Our last one is origin symmetry. So a point up there and a point down there. So our r's are going in opposite directions. Now this is called pole symmetry, or symmetry with respect to the pole, just like it's symmetric with respect to the origin. In this case, we'll have our r theta and a negative r theta. It will also work. And by plugging in our different values of whether we're going to replace our thetas with negative thetas, replace our r's with negative r's, and we can see if our equations hold true. Just like whenever we did our symmetry with rectangular stuff, we plugged in our negative x's or our negative y's, and we were comparing our results. So now let's take a look at several different types of graphs. So we're going to quit sharing here, and we will switch over to here. All right, so our first thing we're going to do, we're going to look at the equation of theta equals something. Now, we saw this the other day. That's going to give us a line going in a certain direction, both positive theta r's and negative r's. So remember that our tangent of theta was y over x. And so if we multiply the x over, we get an equation of y equals tangent of x, tangent of theta times x. Now, in this case, I chose pi over 3. And so if we had from the positive x-axis to our line, that's going to be a 60-degree angle. It turns out that it's a slope of square root of 3, but we get a similar idea behind it. And so with these lines, We can draw slanted lines like we normally do. We'd also draw a horizontal line, at least all through the origin. Now, another way we can do our horizontal lines is with what we have here. Whoops, wrong one. There it is. Let's get rid of that one and bring up the next one. So this C over sine. Now, if we multiply sine over, r times sine of theta is the same as y. So it's like a y equals a number. And if I change my C value, it's going to move my graph up and down. So a number over sine gives us horizontal lines. If we're going to do vertical lines, instead of using sines, we use cosines because r times cosine is x. So we multiply that over, we get x equals something. And as you see with the graph, as we move it left and right, we get our vertical line. Next thing is let's look at circles. So we saw this before, but whenever r equals something, r is square root of x squared plus y squared. And if we square both sides, we get x squared plus y squared equals something squared. That's your equation for a circle centered at the origin, which is what we get. Because here, our radius equals something. So we're always going out 2 units in every direction. It doesn't say anything about our theta, so we're going to go in 2 units in every single direction. And now if we change this r, we can make it bigger or smaller. But no matter what we do, we're still getting a circle. Let's try some other stuff. Now we just saw one like this, but it's r times sine. And we see it's going to be a circle going up. Now, if we change our c value, that's going to change how big it is. So by multiplying by a bigger number out front, we change the size of our circle. But our sine is related to the y value, so it's going up or down. If we go negative, it also go down. If we change to our cosine is x's, so it goes left and right. And we can make it bigger again. And now notice that the number out front is not our radius, though, now. It's our diameter. And if we go negative, we go the other direction. Let's look at some other neat things that happen. So r equals theta. So now, as we're going out, as our angle changes, our value is getting bigger with that theta. So we end up with this really neat spiral, and however far out you go. Now our theta is just between 0 and 12 pi. So in this case, it does stop. But theoretically, if we want to keep going, it will keep going with our spiral. We can modify that spiral by making our theta an exponent or doing other stuff to it, whether we multiply by a number or whatever else. But here, it's going to be an exponent. So our r increases very quickly with our theta. And so now we're going to get into the graphs that we will call limacons. So limacons, Limacone, then S. If we scroll down a little bit more, we'll draw this one. And so we need to zoom in a bit. That is not a limacon. Well, it's a type of limacon. It's a little bit of a more special case. Let's drag that over. Now with a limacon, we're going to have this r equals a plus b sine of theta. But in order for this to happen, our a has to be bigger. So our A is bigger than our B. So I'm going to put B at 0. And I want you to notice a neat thing here. And I'll make this 2 just to make that a little bit bigger. All right, so this is just R equals 2, which is our circle that we saw before. Now with our limacon, we're going to start making our B value a little bit bigger. And notice that it starts shifting up, but it is also now getting misshapen. As we go more, it's going to get more exaggerated. And we end up with this dimple. So this is a limacon without the inner loop. And so as we go further and further, that dimple gets a little more exaggerated. And let me move back a little bit. Come on, just a little bit. There we go. And so this general shape, it kind of gives us like a lima bean, if you want to think of it that way. If you're looking at it, that it comes in, yeah, then it's not quite. Lima bean is a little more exaggerated on this. Although if we get these numbers bigger, we can get more exaggerated shapes. But now as we go up and we get our A and B to being equal, we get what's called a cardioid. Now I'm going to shift this and I'm going to change this to a negative. And I think you can see a little bit better now. At least for the top, we have that heart shape. It doesn't quite come to a point down at the bottom. But that's why it's a cardioid, cardiac type thing dealing with the heart. Cardioid, it looks kind of like a heart. Then if we increase this to make our B being bigger, it's still a limacon, but now we have this inner loop. And as our A value now starts to go to 0, so limacon without the inner loop, A is bigger. When A and B are equal, it's the cardioid. When B is bigger, it's the limacon with the inner loop. And now as our A gets smaller, notice that the inner loop gets bigger and the outer loop gets smaller until whenever they meet, whenever A is exactly 0, we get that circle. So notice this nice continuum that we get. Whenever B is 0, we get our circle centered at the origin or at the pole. As B gets bigger, it shifts into a limacon. Let's zoom out a little bit. Wrong way. There we go. Until they are A and B are the same, we have the cardioid. Now, as A starts getting smaller, we get that limacon with the inner loop. Until our A goes to 0, now it's just R equals B times our sine. And it's just that circle on top. So we go from a circle centered at the origin to a circle through the origin with the same general equation right here. Now, if we switch this, and we make our A something, and we do it with cosine. It's going to be a similar situation, except now, since it's cosine, it's going to go left and right. And we still get that lima bean type shape for the limacon without the inner loop. Then we go to a cardioid whenever they are exactly the same with our A and B. Then as our B is bigger, we get that inner loop. And as A goes to 0, then we get the circle on the side. So again, we still get that real nice relationship being established with this general equation. Next one. These are called our roses. So let's first increase our A. We'll make our A a 1. Does it start getting bigger? And so our A out front is going to control size. Now let's change our N. So that's going to be that's just sine of 1, which is our circle as we saw before. And now notice we get some weird stuff here, but now we stop at 2. And notice that we have this figure here. Let's, wrong way, zoom in a little more. There we go. So starting at 0, as our theta increases, our r is going to get bigger because sine of 0 is 0. But now we trace it up, and we go through here, and we go down here, and then tracing, and then we're back at the beginning. And then we repeat our process. So these are called roses. And notice that my n is 2, and I have 4 roses. When n is 4, I have 8 roses. When n is 6, whoops, 6, 12 roses. When it's 8, 16 roses. So whenever our n is an even value, it's always double the number of petals from what our n value is. But now, if we do 3, we only get 3. 5 is 5. 7 is 7. 9 is 9. So whenever it's an odd number, we get exactly the number of petals as whatever our n is. Although that's not really true. We actually get double them. So, but here's the thing. Whenever we go through here, all right, we're out to our n equaling pi over 2. Then whenever we're down to here, n is pi over, sorry, that's pi over 4 out here. Now it's at pi over 2. But our it's 3 times pi over 2, so it's like sine of 3 pi over 2. So while even though we're looking up, our direction goes down. And then whenever we work all the way through here, when we're looking left, we went through this whole thing just from 0 to pi. If we do it again to 2 pi, we'll go trace this twice. So we always have actually 2n petals. It's just that whenever our n is odd, the petals line up over the other version of it. So we only see, in this case, 3 of them. So you only see half the petals. Now we can also do this with a cosine. And again, when n is odd, we have exactly that number of petals. When it's even, we have double the petals. But notice now our relationship here, that whenever we have our sines, they're kind of crooked, and our cosines line up exactly on the axes. Now, whenever we increase our n, the blue, the cosines, still have something on the axes, and our greens are going to be starting off with a slant. Here again, our cosine lines up on the horizontal axis, and we have a petal lining up on the vertical axis for sine. For 5, we always will line up along the positive x-axis for the cosine, but our sine can sometimes switch between the upper one and the lower one. So, but those are our flowers. Our last one we're going to talk about are called lemniscates. So with our lemniscate, our equation is really r squared equals a squared plus sine of 2 theta, or r squared equals a squared times cosine of 2 theta. And first, let me drag my slider for a down here a little bit so I can control things a little bit better. And now this is always going to be 2 theta. But now let's graph this. And this is the type of thing that we get, this figure 8. And now as my a changes, it's going to make it bigger or smaller. And our cosine looks like infinity sign, exactly on the axes. The sine one is slanted. Cosine is horizontal. Now, our lemniscate comes from the French word. I believe it's for ribbon, is what it is, which makes sense. That's kind of like what it looks like. Excuse me, it's not French, it's Latin. So, but the Latin word for ribbon. So that's where this comes from. I always thought it was a propeller, but whenever these were made, it was before airplanes. So you see where they opted for the ribbon stuff instead. So we went through a lot of different crafts. Your big thing is being able to recognize the equations where they come from. And whenever I can stop sharing this, there we go. And then having an understanding of how we draw these. And then with our circles to the limacons, to the cardioids, to the limacons with the inner loop, to the other circles, how we have that nice continuum in our relationship. So being able to draw them, so knowing and having an understanding of that process, and then being able to recognize what do your graphs look like, what do the equations look like, and then putting them together.